Hello everyone. In this video, we are going to talk about some methods to place records on files. Recall that in a database at the end of the day, right, whatever tables that you are storing, employee tables to a student table and all that, these are actually files. And in many cases, these files are really long. Right? So, for example, if you are trying to design a database system for a banking application, right? A bank can have millions of accounts, right? So at the end of the day, all the tables, tuples that you are trying to store in a database, they have to be stored on like a file on your hard drive, right? So now when it comes to storing files, we have to be a little bit smart about things. And before we get into detailed techniques of how files are actually organized in a database, I thought I'll give you some definitions and a little bit of an motivation on what kind of things a database planner should think about, right? So first, some terminology. So there are two terms here with regards to file organization. One is something called as unspanned organization, and the other one being spanned organization. Remember that a file, a database file, the tuples, they are actually records in a file, right? And now when you are starting to place those records or tuples in a file, right, so you start placing one tuple after the another. And you may remember from our previous videos that a database system, or for that matter even operating system, they try to read or write one disk block at a time, right? And then one disk block can be one sector on the hard drive, or it may be two or three sectors also, right? So given that read write is in chunks of one disk block, so a question arises. Now when you're putting tuples onto a disk block for writing, it may happen that one disk block may not be able to fit in all the may not be able to fit in integer number of records, right? So in that case, we have two kinds of organization. In case of unspanned organization, the rule is that no record is allowed to be split across two disk blocks. You might rather leave the empty space on the disk block rather than forcibly fill it, and then uh, sort of break the tuple across two different disk blocks, right? Now why we are doing it, as we go forward you will let know, right? So because depending on the file organization, when we are trying to retrieve a record, we would want to retrieve the record with maybe just one or two amount of discrete operations, right? So now if you are spanning it, then that further increases, because in order to read the complete record, you have to sort of read some more, right? But we will get into the details, Okay, so that was about spanned and unspanned organization. The next concept is what is known as blocking. So, blocking refers to the number of records that you can fit in one disk block, right? Uh, if you have unspanned records, so that means a record is not allowed to span across two disk blocks until unless the record size itself is so large. In that's an anomaly case. uh, but for unspanned records, and under the assumption that size of one record is always less than one disk block, then BFR, or blocking factor of a file, is defined as floor of block size by record size, right? So that means if your block size is, let's say, 10 bytes, and your record size is 3 bytes, so that means the number of records that I can fit in one disk block is floor of 10 divided by 3, which happens to be 3 records, right? Okay. And then given that, If I ask the question, what is the number of blocks needed for a file, then we'll use this formula: C of number of records divided by the blocking factor. Okay. Okay. So make sure you remember these formulas. They are sort of important as we try to do some calculations. Okay. Okay. So now some file organization techniques, right? So typically, when it comes to databases, you have one primary file organization, which is how your actual records are stored on the disk. And then we usually create some secondary file organization techniques in terms of some kind of an index. Okay. So in this particular video and even the next one, we will talk about primary file organization, and after that, in the next module, we are going to talk about some secondary file organization in terms of index structures, right? Okay. So when you have a file which you need to store in a database, then you basically have three types of files. So one is heap file, the second one being sorted file, and then the last one being hashed file. And the first two ones are pretty straightforward and in fact more intuitive also, but nevertheless, let's cover them. So on a heap file it's basically an list of records. They are unordered, and whenever a new record comes in, you just keep putting one record after the another in that file. Note that the file itself may either be stored contiguously, or it can be broken into pieces and then chained as a linked list, so that all is okay, right? So those operating system concepts, they still hold. But the key thing to note is that it's unordered, and whatever new record comes in, you just keep adding it towards the end, right? So the advantage of this kind of organization is that the insert operation is quite efficient, right? You just go to the end of the file and you put it, right? Uh, but what are the disadvantage? So disadvantage is the deletion. So if you have to delete any one particular record, you will have to first search through the entire file, which is going to be a linear search, and then find that record, and then delete it. And then when you delete it, you may even have to reorganize the records, because if you have one big continuous file as a linked list, and then you're deleting something in the middle, you may have to repack. Otherwise you are going to create uh, holes of unnecessary memory wastage, right? So there is a smarter way of doing it. Instead of doing the reorganization for every delete operation, what typical database vendors, they do is that they don't do the reorganization at the moment of delete. If you delete a record, what they would do is that first they will, of course, they have to search for that record, and then put a flag on, or you mark it for deletion, so that whenever you are searching for that particular record, and if you see that that record has been marked deleted, you still return the valid null answer, but you don't actually go ahead and delete that record and pack the other ones accordingly, right? So the packing is done usually once every week or once every month or something like that, whenever the database is taken offline. Then the database engine, they sort of uh, do something called quote unquote garbage collection, if you will, that it will go ahead and it will purge all these records which have been marked as deleted, and then it will again pack. Something like disk defragmentation. I don't know if you know this. In the earlier Windows, this used to be an option there. Okay. So this is the unordered file. Insert operation is easy, but linear search, of course, searching for any record, it's going to take time. And delete, you can be smart about deleting by just marking that record for deletion, and then doing a purge at the end of the week or the month, right? So that was unordered file. It has got its own advantages. Second is ordered file. Now, in an ordered file, as the name itself tells you, that you have all the records in the file, all those are ordered on a particular ordering field. Remember, again, when I say file of ordered records, I still, similar to the previous case, I'm still not saying that it's just one contiguous blocks of memory. Your file may still be stored as a linked list in your hard drive, but nevertheless, all the records, if you start traversing that linked list from top to the bottom, then you will find those records ordered on any one particular attribute of your file, right? What's the advantage of this? If your file is ordered on a field, and then you're trying to search for records based on that field, then search operation is quite straightforward, right? It's going to be very similar to a binary search, right? Whereas the downside is, the insertion operation is going to be a little bit uh, difficult, because first you have to find the exact position where the new record should go in, and then even shift some records little behind, so that you can insert this record, right? Okay, so that is one, and in order to make things more easier, what people do is that they sometimes leave uh, unused space here and there, so that insert operation becomes a little bit easier. Delete operation, similar to before. If you want to delete, you may have to do reorganization, and in order to get more efficiency, what people do is that you just mark it for deletion, and then do the reorganization at the end of the week or month, right? So classically, these are your ordered and unordered files, right? It's just an example I picked up, right? So over here, this I believe is an ordered file, and this is the employee table ordered on the name attribute. Now, as you can see that files are in different blocks and so on, right? Okay, so ordered files are good, unordered files are also good, but they have their own disadvantages, right? So let's try to see something else, which hopefully can give better performance for both search operation, delete operation, and insert operation, right? So this is something called as hashing, or hashed files, right? Okay, so in these set of slides, I have some introductory slides on what is hashing, but I'm pretty sure you all must have heard about this. So I'll quickly go over them. So in hashing, now each record, you have a key value on which you're going to hash. For example, if you are, let's say, storing all the student IDs, maybe you would want to hash on the roll number, right? And so given a key, you pass it through your hash function, whatever hash function you have, and then I will tell you the location where it has to be stored, right? And then if you are searching on the same key, this attribute, then search is pretty much order one, provided your hashed file is nicely well behaved, right? And if you have collisions, then you can sort of maintain an overflow chain and all that. Okay, so now there are two major categories of hashing techniques when it comes to databases. So one is called as an static hashing, and the other one being dynamic hash, right? So static hashing, uh, as you can guess, the hash function is fixed, it does not change, right? So for example, over here, uh, okay. So here we have an example where the hash function gives 10 unique values, right? And for each unique value that the hash function throws out, we call it as one bucket, right? So if a hash function can take 10 unique values, let's say that some integer mod 10 is your hash function, so it will take 10 unique values, right? So for each unique value you have one bucket, right? So now what will happen is that so whenever you have a file like this, so this I picked up from your Corth textbook. So for each bucket you have a couple of records that are going into that particular bucket. Okay, note that this bucket itself may span across multiple disk blocks, and if there is an overflow going on, that can span across even more number of disk blocks. Okay, so this is another just an example illustration of this. So let's say I have a hash function whose range is m, right? So that means it returns values between 0 to m minus 1, let's say, right? So that means I have m buckets, right? And then what we are going to do is that for each bucket number I'm going to store the block address where records in this bucket are. So let's say keep records keep coming, and then you pass them through the hash function, and then the hash function will tell which bucket those records should go to. And then using this table I figure out that, okay, if it has to go to bucket number 1, I pick the address of the disk block for bucket number 1 and go ahead and store it, right? So initially, I'll start it with just one disk block, and as and when this gets full, I'll keep chaining new disk blocks over here, right? So pretty straightforward thing of mapping an hash function to an actual secondary memory implementation. Okay, so when we are designing hash functions for our hashed files, we need to keep in mind two things. So one is that our hash function should be as uniform as possible, and the second one is that hash function should be random in nature, right? So when I say uniform, that means that each bucket is assigned roughly the same number of key values. Okay, so let's say that we have a list of our students, and we try to hash a student record on the basis of the first character of the student's name, right? Now this particular hashing functions may not be uniform for the following reasons, right? Because student names, some characters are more common. So for example, in the database that we have, let's say letter P or maybe M is more common, or letter S is more common in or letter A is more common, whereas other letters such as Z, X, W, they are not so common in Indian scenarios, at least, right? So now if you're trying to hash student records on the basis of the first character of their name, then your distribution of the hash function, it's not going to be uniform. Okay, let's take another example. Let's say that you want to hash the records on the basis of their salary, right? And let's say that the minimum salary is 10,000 per month, and let's say the maximum salary is 90,000 per month, right? So let's say that we design a hash function where we say that all salaries between 10,000 and 20,000 will go to bucket 1, from 20,000 to 30,000 it will go to bucket 2, and so on, right? So this kind of a hash function, this is uniform in the sense that the key values are going to be spread uniformly. But the thing to note is that this hash function is not random in nature, because let's say that the salary of majority of the employees is in the range of 50,000 to 60,000 per month, then all those records will actually be forced into the same bucket, right? And which will lead to overflow, right? So this is an example of a uniform hash function, but not an random hash function. right? So when I say that a hash function is random, I mean that each bucket will have same number of records assigned to it irrespective of the actual distribution of search key values, right? So there is a subtle difference between a hash function being uniform and a hash function being random, right? So in our first case, when we were hashing all the student records on the basis of the first character of their name, right? Then that was not even uniform, for the simple reason that let's say that in our universe of this student names, I have more names like Ashish, Aaron, Anurag, right? So if more names are starting from the letter A, then I'm not uniformly distributing my search keys across all the buckets. So that is the non-uniformity. The random part being that in the case of salary, the salaries are unique, but if the data distribution is such that I had more number of people in the salary range of 40,000 to 50,000, then they all will be going to the same bucket, right? We don't want both. We want a hash function which uniformly distributes the total possible uh, space of search key values, which is coming from uniformity property. And then from the second property, what we need is that even in that uniform spread of the search key possible search key values, if some search key values are appearing more in number, then they should also not be forced onto a single bucket, right? So when both of these things happen, then we'll say that our hash function is both uniform and random, right? Typically, the hash functions, which are used, they are much more complicated. They are not like mod 10, mod 20, or something like that. They go into the inner bit representations of the search key, and then, they do some fancy things. In this particular course, we are not going to go deep into hash function constructions. We'll start with something simple only to illustrate. Okay. Okay. I think I covered this before also. Whenever collisions happen in hashing, uh, we'll we'll try to maintain some kind of an chaining to address those collisions. Okay. So just to show you an image, right? This is how an hashed file may look like. So these are actually buckets, right? So this is bucket number one. It has some records which came here, given some kind of a hash function. And then, if this was overflowing, then, you sort of use some overflow buckets. Okay. Okay. So now let's try to evaluate the static function hashing which we just studied, right? So first, what is the time required for search and insert operation, or maybe delete operation also, right? But mostly let's do first search and insert, right? So searching, if you are searching on the key on which your file is hashed, you are pretty much guaranteed an order one operation until unless your hashed file is in a very bad shape. That means, your hash function was not good, and then there was a lot of overflow, then this search operation will go bad. Insert operation, again, if your hash function is reasonably good, both of these operations, you can do it in pretty much constant time. Delete operation, this is always a mess. If your buckets are such that you can if you want to delete a record, you search for that record and you delete it from the bucket, right? So deleting maybe few records here and there is not going to be creating a problem. But if your file is such that you have some massive amount of delete operations, then what may happen is that your buckets start to get empty. Then you'll have to do some reorganization and all that. Okay. Okay. So in static hashing, as I said, the insert operation, search operation, they are good. They can easily be done, and that's not the main problem with static hashing. The main problem with static hashing is the static nature of the hash function which you are using. Recall that in a static hash, you are fixing the hash function ahead of time, right? And not only it's hard to come up with a good hash function, on top of it you are also fixing it right in the beginning, whereas your databases, they can grow or shrink with time. So for example, even if your hash function was random and uniform and all that, in the initial case, let's say your hash function was such that the number of buckets that it could span across was too small, and suddenly now your file grew maybe 10 times. Then what will happen is that no matter how good your hash function is, you will still have a lot of overflows, and your search performance and even insert performance, they all will go bad, right? And then the flip side of it, let's say that you made a very bad estimate on how much your file size would be, and then let's say that you had a much fewer number of records. Then what will happen is that uh, a lot of space will go waste. So for example, let's say that you decided for an hash function of key mod 100. So by just the virtue of key mod 100, you created 100 buckets and you sort of reserved the space. But then you are not let's say that in the initial phase you did not get so many records. Then what will happen? You are going to waste a lot of space on your hard drive, right? So as I said, the problem with static hashing is the static nature of hashing, right? And the databases grow and shrink with time. So you should be, your approach should be such that it should adapt with the file size. And if you don't adapt with the file size, then what you will end up with is that you may have to do periodic reorganization using a new hash function. Let's say that I start with k mod 10. Once that is filled up, then I have to and then we go into too much overflow, then I have to sit and rehash all my records with maybe k mod 20, and then I have to keep on doing reorganization using a new hash function, if I'm very conservative about things, right? So this is not a very good idea, right? Because every time you do a reorganization, you have to take down the system. The system will go offline for the period of the whole reorganization, right? So the lesson over here is that your hash your technique should be such that uh, it automatically changes the hash function as your database file is growing or shrinking. Okay, so there is a class of techniques called as dynamic hashing techniques, and um, so the techniques in this class, what they do is that as your file is growing or shrinking with time, it dynamically changes the hash function without you requiring you to do the periodic reorganization, right? So there are two very well-known dynamic hashing techniques. So one is called as extendable hashing, and the second one being linear hashing. So in this course, I'll cover only extendable hashing, and we'll not cover linear hashing in this course for the sake of